Binary, one of, if not the most important number systems for computers and technological advances. I bet a lot of you viewers have seen it in YouTube videos, memes, movies, or anything to do with hacking. But before we get too hasty with the ins and outs, we need to ask an important question. What even is a number system? A number system is a system that follows a specific order of rules and expectations. Number systems are fundamental to express and differentiate different numbers from the rest. They can range from systems like the Roman numeral system, which is an ancient system, to the now modern-day binary system. Now that we know what a number system is, let's try and understand how the binary system works. In binary, there are two key terms, on and off. On is represented by 1 and off is represented by 0. When we arrange these ones and zeros in a specific pattern, the place value of them matters a lot. For example, at the start of a binary string, if the first number is a 1, then that means the number is negative. If it's a 0, that means it's positive. We will go more in depth on the binary system later on in the video. Now that we know about number systems, let's talk about the history of binary and how it came to be. The binary system is one of the earliest known computing systems in all of history. It has been used since the 17th century and still stands as the main computing language for all computers today. In many different periods of history, the fundamental binary have been shown. Dating back to as early as the 9th century BC, a book called I Ching contained an arrangement of hexagrams that followed the binary pattern. Later in the 17th century, polymath Gottfried Wilhelm Leibniz made an article titled Explication de l'arithmétique binaire. This article by Leibniz was the catalyst for the binary system that we now know today.
Now that we know the history, let us move on to the meat and potatoes of binary, how ones and zeros can really be used for whole computers and how systems interpret it. The first things we should learn are the basic terms of binary. A bit is a 1 or a 0, the most notable part of binary. A byte is 8 bits in one line. So, for example, we could have 1 0 1 0 0 1 0 1, and that would be a byte. Since we now know the building blocks of binary storage, we can move on to the most notable storage sizes and how they relate with binary. The smallest one of these is called a kilobyte, which is 1024 bytes, or in other words, 8,192 ones or zeros. In today's world of videos, a 30-second video is 65,000 kilobytes, or once again, in other words, 65 megabytes. A megabyte is 1 million bytes, or 8 million ones and zeros. The next size up is a gigabyte, which is 1 billion bytes, or 8 billion ones and zeros. To put that into perspective, if you lived for 8 billion seconds, you would be 254 years old. If you took 8 billion steps, you would go around the world 139 times. And finally, the biggest size, a terabyte. The most you would ever need for all your videos and photos. It is 1 trillion bytes, or 8 trillion ones and zeros. Now that we know the terms, we can move on to translating binary. Let us start small. The basic binary decoding. No decimals, just pure whole numbers. The way this works is by going from right to left and increasing the exponent by 1 each time starting at 0. The base for this exponent is always 2. Using this system, we can create almost every number we have the available space for. An example of this would be the translation of 101101. Think of 1 as yes and 0 as no. The number starts with a 1 in the first place, which is equal to 1. This means we add 1 to our final total. The next number is a 0 in the second place, which is equal to a 2. This means we do not add the 2 to the total. The numbers after that follow the same principle, and if you're wondering what that number is, I will give you 1 minute to decode it. Good luck.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Before we move on to the answer, it would be great if you gave a like and a subscription to my channel. Thank you. Back to your scheduled video on binary. Time's up. The answer was 45. Give yourself a pat on the back if you got that one. But now it's time to move on to the more extreme translations. Well, now you're probably wondering, how do you make decimals or anything that's not straight whole numbers? Well, this is where the 32-bit floating point integer comes in. This allows us to do negatives, decimals, pretty much anything we ever need. Okay, so let us start with the basics of this system. As the name implies, this system has 32 bits inside of it. The 32 bits are broken up into 3 separate parts: the sign, the exponent, and the mantissa. The system is also called the IEEE 754 converter. Now that we know what we are working with, let us start with the sign segment. In this 1-bit system, a 1 represents a negative and a 0 represents positive. That's it. No value, just tells us what sign it is. Now it's time for the exponent. Think of this as an 8-bit segment, going right to left, increasing the same way I showed previously. This segment ranges from 0 to 255. Now once you have that number, subtract 127 from the total. This allows us to have negative exponents, which will come in handy later. So for example, if our exponent would be 10110101, which is equal to 180, we then subtract 127 to get 53. 53 would then be our final exponent. Now the final segment of our integer, the mantissa. This works a little differently because it has 23 bits and goes from left to right. Instead of going up in power, we go down in power. For example, we start with 2 to the power of negative 1, then 2 to the power of negative 2, and it goes on in that fashion. This number will always be below 1, so to account for that, we add 1 to our final total. So for example, if our number is 1011 followed by the other 19 zeros, that would be equal to 0.6875, but then we add 1 to our final total, so it would be equal to 1.6875. Now for the formula that actually ties our number together. The formula is the mantissa times 2 to the power of the exponent. Then our sign decides if it's negative or positive. If we took our previous examples and shoved them into our formula, it would be 1.6875 times 2 to the power of 53. Now, this is a really big number, so I didn't expect you to try to answer it. But a few rules to take away. A 0 in the exponent and no value in our mantissa represents pure 0, negative, or positive. 255 in the exponent and no value in the mantissa represents negative or positive infinity. Now it's time for our test. The test number is the following: 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, followed by the rest being zeros. I will give you 2 minutes to solve this. Good luck, and remember to separate your segments. All right, time is up. Now, this was a hard one, but the answer is negative 6.5. If you got this one, you are a binary master. Now it is time for text, the most annoying part of binary. Now, text is all memory. It uses a 7-bit system to represent numbers, letters, and symbols of all kinds. The table will be shown on screen shortly. That about wraps up my part on this video. Thank you for listening, and I hope you learned from my explanations. Let's move on to the next segment of the video.
Now that we know what binary is and how it works, we are going to look at how binary is used in our everyday lives. Binary is more than just a number system. It is the foundation of most, if not all, electronic devices. Every second, a collection of zeros and ones are being transmitted across millions of devices. From the second a device turns on, binary signals are being sent, received, processed, and packaged to run its software and communicate with other devices via Wi-Fi. We can thank binary for our phones, apps, internet, and storage. Our computers and phones are constantly using binary from the moment they are turned on. Binary in electronics are sent as high and low voltages across wires, with a high voltage representing 1 and a low or no voltage representing 0. A physical button corresponds to 1 bit. When the button is pressed down, it sends a high voltage signal which represents a 1, and when the button is released, it sends no signal, which represents 0. The CPU, or Central Processing Unit, knows what to do with these signals. The CPU in phones and computers is responsible for fetching instructions from its memory, decoding it to understand what to do, and executing the instructions to the entire system. Billions of tiny transistors are switched on and off, telling the rest of the device what to do. These instructions are written in binary, and they are called machine code. Displays are also made possible with binary. They use the strings of zeros and ones to decode brightness and RGB values for each pixel on the screen. Computer programs and operating systems all rely on zeros and ones. When a program is written in a coding language that humans can understand, like Python or C++, it must be translated into binary so the CPU can understand and send it with on and off signals. The CPU uses these signals to manage memory and allow multiple programs to be running at the same time. When an app or software is open, the operating system loads the binary data into its memory and tells the CPU to execute it based on the binary instructions. Updates to apps or operating systems just boil down to changes within the binary instructions. Everything that a computer and a phone does is dependent on their binary code. Binary data being sent over long distances is the reason why the internet is possible. The information of messages, videos, and website URLs are all packaged into binary code. Every letter, color, number, or instructions are all packaged up. These packages of binary are sent across devices. This can be via electrical signals in cables or radio waves in Wi-Fi. Once the package reaches its destination, the device reassembles it back into whatever was being sent. Systems that check for errors in the transmission use binary to detect and fix any issues. This helps online communication become faster and reliable. Digital storage allows all information to be saved using binary. Documents, images, videos, text files, and applications can all be saved as a long list of zeros and ones. Each 0 or 1 is saved as 1 bit, and a byte is equal to 8 bits. A bit is the lowest form of storage possible. An image can range from just 100 kilobytes to 10 megabytes. 1 megabyte is equal to 8 million zeros and ones. Even the smallest change to a video or image on the outside can mean that millions of zeros and ones would have to be rewritten. Temporary memory is only a few items that are brought to the CPU for immediate use. This is also called RAM. For example, when you open a browser, the tabs and browser data are all copied from the SSD to the RAM for easy access. Once the computer is turned off, all data from the RAM is deleted. An SSD is the permanent storage device for your computer or phone. All programs, images, videos, and files are stored there until the user deletes them manually. When files are deleted from the SSD, it doesn't mean they are truly gone forever. The file is removed from the directory so you can't see it, and is only marked to be overwritten by new files. So the file isn't gone until it is overwritten later on, or you use a special tool to either replace the file with random zeros and ones, or shred the file into the same thing. The only foolproof way to truly get rid of files is to physically destroy the SSD or flash drive that it is stored on. In conclusion, binary is the foundation of modern digital technology. From our phones and computers to digital storage, programs, and instructions, it is all made up of zeros and ones. It explains how reliable and fast our computers and phones can be. Understanding what binary is and how it's used in the digital world explains how a lot of stuff works around us.
Up until now, you've been hearing about something called binary, which is the language computers use to communicate. At first, binary can look confusing, just a bunch of zeros and ones that don't seem to mean anything. But the important thing to remember is binary is actually very simple. Instead of using lots of numbers or letters like humans do, computers only use two choices. They constantly are asking one question: is something on or off? When something is off, we call that a 0, and when it's on, it's 1. Every number, every letter, every image, and even this video can be broken down into these small 0 and 1s. And now that you understand the basics, it's time to actually use binary and not just hear about it. So let's play a quick game, and we'll see how well you understand binary. The game you will be playing is called Decode the Binary. There will be 5 rounds, and each round will get progressively harder. You might be asking yourself, how does this game work? This game works by letter, number, or word that will be popping up in binary. You can pause the video if you need more time. You can also count your scores and compete with others to see who gets the higher score. Now let's get started with the first round, which will be the easiest one. Round 1. The first binary code is 1001. This one is just a single digit number. The answer is 9. Round 2. The binary code is 10000011. This binary represents a number. Take a guess. The answer of this one was 67. Round 3. The first binary code is 01001000. This binary code is one letter. The answer was H. Round 4. The binary code is 11110100. Another single letter. The answer for this binary was D. Great job decoding those binary messages. Now that you've seen how binary works on both numbers and letters, it's just time to see how much you actually remember from our video. Let's do a quick quiz to review the history of binary, how it works, and where we use it. Let's start the quiz. Question 1. Who is often credited with developing the modern binary number system? A. Isaac Newton. B. Leibniz. C. Albert Einstein. The correct answer was B. Leibniz developed the binary system we use today for computers. Question 2. In binary, the value of each position doubles as you move to the left. If the rightmost digit is 1, what is the value of the thirdmost digit to the right? A. Number 2. B. Number 4. C. Number 8. The correct answer is B. Binary places values go 1, 2, 4, 8. It doubles each time you move to the right. Question 3. In binary, each place values doubles as you move to the left. True or false? The answer is true. This is how binary represents number with the power of 2. Question 4. Which of the following represents how binary is represented in electronic devices? A. By using letters and numbers that are stored in the device's memory. B. By using high and low voltage to represent ones and zeros. C. By storing information only as text and images. D. By sending data only through with Wi-Fi signals. The correct answer is B. Electronic devices use electronic signals that run across wires to send and process data. If you got those quiz questions right, that means you now understand the basics of binary, how it works, where it's used, and why it exists. Do you remember the glitch text at the beginning of the video? That glitch was actually written in binary. The screen was filled with ones and zeros, and it looked like something had gone wrong. But that wasn't a mistake. It was a message hidden in plain sight. Decoding the binary reveals a sentence. The sentence was, rate our video out of 5 stars with the exclamation mark at the end. What started as a confusion turned into something you understand, which is exactly what learning binary is all about. Binary may seem complicated at first, but it's really just patterns, logic, and simple math. Now you know the system computers use to store text, images, videos, and even this presentation. So now that you can read the message, we'll leave the final decision up to you. Using what you learned today, rate our video out of 5 stars. Thank you for watching our presentation.